Okay, so today we will learn on power system state estimation. Okay, so last unit it is preventive, emergency, and restorative controls. Under that, so previous lecture we in lecture one we've just gone through we have revisited the operating states. Then under that I have said that we have to carry out the power system state estimation, which means so now based on certain condition you have to estimate which state power system is operating. There are 5 states we have learned, so now we have to estimate. How to estimate? So we learn today. Okay, that is known as power system state estimation. Okay, so here it means we will be estimating which operating state power system is which operating state power system is at. Okay, so example like it is normal state. When you will call normal state, you know the definition, but how to carry out the estimation? Then alert state, then emergency state, then in extreme state, and then restorative state. So we have to know this. So now we will carry out the power system state estimation in today's lecture. Okay, so our objectives of today's lecture is the fundamental of power system state estimation. What are the fundamentals of power system state estimation? Basically, there are 2 ways which we can carry out the power system state estimation. One is static, another one is dynamic, so which we will learn later on. Then handling errors and bad data in static state estimation. So when you carried out the power system state estimation, so now if somebody give a different data, then there will be error. How to handle that? Or we call it as a bad data in the state estimation we'll carry it out. Then this static state estimation has certain limitation. Then we'll go for dynamic measurement, and then so we'll see. Okay, so if you are able to understand these 3 objectives, then it will be more than enough for today's lecture. Okay, so first, power system state estimation. So now what is mean by power system state estimation? And then there are 2 types of power system state estimation, static and dynamic state. But first, let's see what is mean by power system state estimation. Okay, so power system state estimation. Actually, this power system state estimation is a process. Okay, it is a process whereby you will collect a data from the measuring point and send to the central computer and can be formed into a set of reliable data for controlling and recording purposes. Okay, so if somebody asks, what do you understand by power system state estimation? So actually it is just a process where you will collect the data from the network measuring point, which means, so example, you want to have a data generation data. So you will collect from Chuka, example, in Bhutan, Chuka, Tala, Kurichu, and all. Okay, you collect this data and send it to the central computer. Means, so here central computer in Bhutan it is BPSO. So BPSO will collect the data, generation data from the Chuka, Kurichu, all generating station, and then it will record in the BPSO. Okay, load dispatch center we have learned, right? In that, and then also this BPSO will collect the data of the transmission line and then all, and this data will be used to or can be formed to set a reliable data, or this data will be used to control and recording purpose, which means based on this data then you will estimate the power system state. So now if everything is normal, then you can say it is in normal state, no need of any measure or control measure we have to take off. But if it comes out to be based on that data, if it comes out to be emergency state, then what control measure you have to do? So that control measure we have to perform, which we will learn in later lecture. But this basically this power system state estimation means it is a process whereby you will be telemetry data, means you will collect from longer distance or from network measuring points to a central computer and can be formed into a set of reliable data for control and recording purpose. Okay, this is a definition of power system state estimation. Okay, and how to carry out power system state estimation? basically there are two ways which we can carry it out. One is static state, another one is dynamic state. So in static state, how you can do is you will take or obtain the measurement or obtain from measurement, but within a time interval of about 0 to 5 seconds. Okay, which means all the data you will get within a 0 to 5 seconds. That is known as static estimate. Okay, it's a data obtained from measurement taken within a time interval of 0 to 5 seconds. Okay, and then in dynamic state, what you will do is it has to be measured. This data measured in a relatively shorter times, means say 0.01 second. So which means within 0.01 seconds, so you have to get all generation data or transmission data or transmission line data, such type of state collecting data and then estimating the state of the power system is known as dynamic state estimate. Okay, so but in static, there's option, you can keep 0 to 5 seconds. So within, okay, so you do not specify, but within 0 to 5 seconds, you should get that. But whereas in dynamic, 0.01 seconds, so example, within relatively shorter time, it's 0.01 second or 20 millisecond, they will say that within that second, I have to have a transmission line data, which means you will get that. If you get that, that type of power system state estimation is known as dynamic state. So normally, this static state will commonly, okay, we will provide the steady state snapshot of the system, which means, so normally if you are trying to estimate the power system state estimation by static state estimate method, then normally you will get the steady state snapshot of the system. Okay, whereas if you carried out the dynamics, so you know that it will be at during transient time and all. Okay, so this one we will see that. Okay, so then this is, okay, so we'll discuss in next slide how to carry it out. So in this slide, you have to know what is meant by power system state estimation, how to carry it out, static and then dynamic. Okay, so with this, so now let's say first one, static state estimate. Okay, how to carry out a static state estimation procedure. Okay, so you know that if you carry out the static state estimation or estimate, so normally you will get the steady state snapshot of the system. Okay, so now first let's try to see static state estimation procedure, how to carry out the power system state estimation by the method of static state estimation. Okay, so first let's consider this diagram. Okay, consider a simple diagram here, and then let's assume that in this one we can measure sending end voltage or receiving end voltage, or let's say P1, Q1 can be measured, then P2, Q2 can also be measured, we can, right? And X and the RO, so we can measure or we can know that, and then V1 and V2. Okay, which means here power at the bus, real power, reactive power, voltage at the bus 1 can be measured, and then at the same time power, real power, reactive power, and then voltage at the bus 2 can also be measured. Okay, we can measure and then record it. Okay, so which means here in the system we have obtained the following measurement, means we'll measure and obtain that P1, Q1, P2, Q2, V1, V2. Okay, and line and the line magnitude at 2 ends, means here in this 2 end or 2 bus we can measure bus 1 and bus 2. But only unknown thing here is we will not be able to measure this one, del 1 and del 2. Okay, so this is unknown. If this is known, then we can say that which state power system is operating. So now here del 1 and del 2 we cannot measure here. So now if you know these two value, then we can say that which state power system is operating. Or okay, so we can know that. So now here if del 1, del 2 is known, then system is fully estimated. Okay, which means we can estimate and say that it is in the alert state or normal state or emergency state. But normally we cannot measure del 1 and del 2. Or you know how to measure. Reactive power, okay, you know which device we will use to measure. Then voltage also you know which device you can use to measure. But del, as of now, Okay, so later on we'll see, but in static state or at current state, we don't have a device to measure del 1 and del 2. But if we know this del 1 and del 2, then we can say that we have fully estimated the power system, which means based on this value of P1, Q1, P2, Q2, V1, V2, and del 1 and del 2, we can say that which state power system is operating. Okay, so now we assume that the parameter of line are non-fairly accurate, which means when you measure this, you have taken accurately P1, P2, and P1, P2, Q1, Q2, and V1, V2. But del 1 and del 2 is unknown. Okay, but if we know this value, P1, Q1, P2, Q2, V1, V2, so we can find del 1 and del 2. How? So now if all as, and then we assume that this P1, Q1, P2, Q2, and V1, V2 are accurately noted. Okay, then if you know this, then we can find del 1 minus del 2 quite easily by following formula. We know this formula, basic formula, right? So here P1 can be given by this equation, right? P1 will be equal to V1 square cos phi by z minus V1 V2 cos phi plus del 1 minus del 2. So now here everything is known except del 1 minus del 2. Phi, okay, V1 is known, we have measured, V2 is known, P1 is known, Z we can know by this Z equal to R plus JX, and then phi can be known is tan inverse of X by R, right? Only unknown here is, unknown parameter is del 1 minus del 2. So now using this formula, we can calculate the del 1 value of del 1 minus del 2, and then we can, now if we know the value of del 1 minus del 2, then we know that the power system state is fully estimated. So now, so here, however, if there is a measurement error, but we have to be take note of it. If you have an error in measurement in P1, V1, or V2, then del 1, del 2 will be inaccurate. See here. If you have not measured P1 correctly, okay, then V1 correctly or V2 correctly, so then what you will find is, so you will not get a accurate, okay, you will not get the accurate power system state. Okay. Okay, so now if you are not taking reading of P1, V1, and V2 correctly, then you will not get the correct value of del 1 minus del 2 or del 1 del 2. So which means, so we as engineer or particularly goodness, we never take the reading accurately, right? If it comes 1.01 something, then you will assume that 1 is correct one, right? But if you do like this, so it says that you will not get the accurate one. So now what it says is, so it is best to cross-check the result with the formula. So if you use just this formula, and then if you try to do that, so now if you have not recorded this correctly, or let's say P1 value is 0.001 per unit, if you have like this, then what we do is this 0.01 is very small, so let's neglect it and you take 1. Similarly, you will take this. So now what you have to do is, if you use this just single formula estimate, then it says it will not give an accurate power system state. Okay, so then what it is to do is better to cross check with other formula. So this, now you have measured P1, right? Then you can go for Q1 also we have measured, then Q1 formula will be given by this, except del 1 minus del 2 is not known. Then P2, all for this 4 value, you substitute and then try to find del 1 minus del 2 or del 2 minus del 1. And then if this value of del 1 minus del 2 is consistent, means let's say del 1 minus del 2 you got is 30 degree. So by our formula, using this formula P1, using Q1 formula, P2 formula, Q2 formula, if you get 30 degree, then we can say that you have estimated the power system state correctly. But if any one formula, okay, you have, let's take example, P1 has got a 29 degree, then from Q1 you got 25 degree, P2 you got 30, Q1 you got 30. Then we cannot say that you have estimated correctly. You have estimated, but you have not estimated correctly. Okay, so then what you have to know is from all this formula, you have to get the same value of del 1 minus del 2 or del 2 minus del 1. It's just the same, del 1 minus del 2. If you get 30 degree, then del 2 minus del 1 should be minus 30 degree. So you have to get like this. So now just for example, what I said is, you take this r plus jx, r is 0.1, and x is 0.1. Then check that the following set of measurement will give the consistent value of del 1 minus del 2. Assuming that P1 you have measured 5.1, P2 minus 4.82, Q2 0.83, and then Q1, Q2 1.82, V1, V2 1.1. So now you try to substitute in above formula all this value. First use P1 formula, substitute whatever it is there, then you try to find del 1 minus del 2. Then you substitute for P2, so P2 value is known, substitute here, V1 is known, V2 is known, then phi you will get that tan inverse of x by r, they all you substitute here, and then you try to verify that whether you are getting this V1 minus, del 1 minus del 2 is equal to 30 degree or not. Okay, actually it should come, I've solved and then make it, but I have not solved for individual. You substitute all value of P1, P2 in respective formula, and then you see that by using the P1 formula, whether you are getting 30 or not, then using Q1, whether you are getting 30 or not, P2, whether you are getting 30 or not, and Q2 formula, whether you are getting 30 or not. See, if it comes out to be 30 from all, then we can say that it is fully or correctly estimated. Okay, so now what it happened is, so you use this all, and then if this del 1, del 2 obtained using different expression, we have 4 expression here, expression are inconsistent. One get 30, one get 28, like this. It means that error exists in one or more of the measurement. So now, if you're not getting 30, okay, in that example, what do you mean is, either you have made mistake in the measurement of Q1, P1, or P2, or Q2, or V1 or V2, which means there exists one or more error exists in one or more of the measurement. Okay, so then what you have to do is, so now in that also we can go there. Okay, other step are there, but what it means is you have made some mistake in the measurement. Okay, so then what you can do is, say example I have given is, more of the following set of measurement have some error. So now just I have given example, not earlier one. Earlier one example it will give 30. Okay, you try to solve this. Okay, you will get 30, but here just to show that if there is a error in this measurement of this P1, Q1, V1, and V2, then you will not be able to estimate the power system accurately, power system state accurately. So now see here, if you use this and then you try to substitute in above 4 formula, P1 4.8, Q1 0. V1, V2 this value, and then tan value you will get same R and the X value you use. So del 1, del 2, from one equation you will get 28.19 when substituted in P1. Okay, but you will get minus 17.96 when used in Q1. So from these two formulas itself, you can say that you are not getting consistent. Actually, del 1 minus del 2 should be consistent, either 28.19 or minus 17.9 degree. You have to get this, right? So then what we have to know is, then you have to know that we have made some error in the measurement of P1, Q1, and P2, Q2, or V1 and V2, which means we have not recorded the data properly, or your instrument have some fault. You have to know that. Then in such case, so now this question will arise. How do we get the correct estimate of del 1 minus del 2? Okay, so how we will get that? So that is known as error handling, or handling errors and bad data in static state estimations. Handling errors and bad data in static state estimation. How to handle such case? Because that let's say 1 to 2 p.m. Thursday, so that means time 1 to 2 may come, but day will not come back, right? Already you have recorded, and then you have recorded wrong. Then how to handle such type of error, or we call it as a bad data, because you have collected the wrong data, so you have to get, that's why it is called it as a bad data. How to handle in is static state estimation. Okay, so then one possibility is to take the average of this del 1 minus del 2. So using one formula, you got 28.19. Then using another formula, you got minus 17.96. Then you use another formula, P2 and Q2, you will get another del 1 and del 2. So then what you can do is, you try to carry out the average. Or one possibility is to take the average of del 1 minus del 2 obtained from the formula for P1 and P2. First, you try to calculate the del 1 and del 2 from the substituting in the P1 and P2, then you take average. Okay, this is how we have to handle the data error data. Okay, but this way one does not place too much faith on one measurement. So which means we are not giving much faith on one measurement data only. So you try to take this average, or you take all four and then take average it, and then you take that average as a del 1 and del 2 value, and then you try to estimate that. But this also has some problem, right? We have averaged it, and it has not giving the accurate one. So now what you have to do is, other way to carry it out, instead of taking averages, you try to obtain the value of del 1 minus del 2 by using the concept of minimize the falling error. So which means we have to go back to the optimization concept. Okay, optimization concept, you have to take this, and then you know that minimize this j is equal to, you introduce one constant k1 into p1 and square it. Okay, this is a basic formula how to handle the bad data or the error handling. And then k2 into q1, whatever formula you have, you square it, plus k3, and then all four data you try to do this. Okay, substitute here, and then what is k? Okay, we have to minimize this, and what is k, where k1 and k2 and k4 are positive weights. Okay, it says it is a positive weight, and then j is always greater than or equal to 0, it should come. And then you have to use the concept of optimization, that is minimization of j result in this square deviation from this measure value. So when you minimize this, what it will do is, it will result in the least square deviation from the measure value. But again, in these formulas, one main problem what you face is how to choose this k1 and k2, k3, k4. This is a question, right? So main problem, however, is to choose the weights k1, k2, k3, k4 appropriately. Okay, so now how to choose that is another problem which we will face in handling an error or bad data in static state estimation. So how we will choose is, so now if you find a similar quantities, power, reactive power, one can choose weight to be equal. So now it depends on you. If you choose one, so all should be one, but for similar quantities of power. So means when you measure the power, if you come out to be similar. But again, it is a problem. But what you can do is very accurate data you will get is this. Use this concept, optimization concept, which we have already introduced in unit 4. Okay, minimizing J requires us to use an optimization process as outlined in the previous unit, that is unit 4 we have learned. Okay, so then what it says is still this static state estimation has some problem or a disadvantages or a problem. Both the approaches, first one what you have done is you try to average this and find out the del 1 minus del 2. Second, what you are trying to do is you try to minimize. Why we are trying to minimize? Because we are trying to minimize to deviate. Okay, so least square deviation from measure value, or least deviation from the measure value, minimize it, are likely to work well if errors are small in magnitude. Which means if this P1 and P2 value which you have to measure is very small error is there, then this will work. But if you have, okay, by mistake you have done a huge mistake in the collection of this data P1, P2, Q1, Q2, V1, V2, then this type of solution which I have explained, one by minimizing, another by averaging, will not work. Okay, it will only work for error in a small magnitude only. Okay, so then what we have to do is there still exists gross error in the data, okay, which occur and say due to failure of communication, then above approaches may fail. If there is a huge error in your data collection, then this method will not work. Okay, your approaches above these two approaches will fail. So then how to go about this? Okay, so here before we go about this, so now you try to see here. For example, if the measure value or P1 is this much, P2, see here. Normally you will not have P2 value 0. Okay, just as an example to make it clear, I have given here P1 is 5.1, P2 is 0, Q1 is 0.8, Q2 is 1.82, V1 1, V2 1. Then it is obvious that some major flaw exists in the data. Normally, you will not have P2 0, you have P2 1, but how it will come out to be P2 0? Sometimes when we collect the data, okay, so sometimes we make this, right? This type of errors. There is a huge flaws or major flaw exists in the data. So in such case, above two method, averaging and then minimizing will not work. So now can you find a reasonable way to identify gross erroneous measurement or bad data detection? Okay, so which means now we have to ask our question to ourselves, can del 1 and del 2 be estimated individually? And why we have to estimate, you know, how we will estimate. Okay, so that's why now, okay, nowadays, so different technique, that is dynamic measurement or dynamic state estimation is going on now. Wide area measurement, actually it is in the, actually we are using this static state estimation as of now, but this one is a new concept because this many flaws has been found out, fault has been found out, and then they are trying to develop another way. So there's dynamic measurement or dynamic state estimation, or we call it as a wide area measurement. And using this measurement, what we can do is we can measure the del 1 and del 2 value individually instead of del 1 minus del 2. Just here what you can do is no need of recording the all value, we have to record all value. No need of substituting this P1, P2 value and then find out del 1 minus del 2. What you can do is directly you can measure P1, P2, P3, and then Q1, Q2, V1, V2, and then you can measure this del 1 and del 2 individually. Okay, so how we will measure is using a satellite. Okay, so satellite, but this is a new concept which is developing in the power system. Okay, so this state or dynamic measurement is known as dynamic state estimation, which will allow the data acquisition at a faster rate. Already we said that dynamic means 0.01 second, other one 0.5, 0 to 5 second. Here, example, you will give within a cycle of 20 millisecond, you will get a data. Okay. Okay, this data can be obtained from various locations which may be geographically apart. So, which means, so you will get the data within 20 milliseconds, then within a cycle of 20 milliseconds from Chuka, Kurichu, all. Okay, because these power plants are located in different geographical area, right? So, but within 20 seconds we'll get, but how? Using a satellite. Okay, so later on I will explain about this. But at this same time, okay, since data is measured and transmitted at a faster rate, it is possible to capture changes they evolve in a time. Okay, what changes it take place within a second, it will able to capture. Okay, these measurements are also synchronized. Okay, it will be synchronized, and then this synchronization will be made possible by common timing signal. So all will have a common timing signal. okay, to various measuring unit at different location via satellite. So here we will be using satellite. So means it's almost becoming like a space technology, but which will measure all the data, and even you will measure that angle del 1 and del 2 individually, and then we can estimate the power system state. So this static state estimation has a lot of error, problem or disadvantages. So then now it has been developing this type of thing. Okay, so then this state estimation measurement are usually not synchronized. Basically, it will not be synchronized, and phase angular difference are obtained not by direct measurement. Right? What you have to do is you are not getting from direct measurement, but you are substituting in the basic formula, or but estimated from the real and reactive power measurement. First, measure the real and reactive power, substitute their the value, and you try to find this phase differences, angular differences in static. Whereas in dynamic, you can measure individually and you can estimate, but using a satellite. Okay, so just example here. Okay, so now we can say that in this figure, so I will explain with this figure. Here it will have a load dispatch center. Okay, and satellite provide the timing pulse here. Okay, you have to use a satellite, and then your grid will be somewhere here, and then your location 1 is here. Means let's say Chuka is here, and Tala, or let's say Tala, Urichu, then Dagashu will be here at different location. Now what you can do is from load at the load dispatch center, what you will get is all data of sugar you will get here within a 20 millisecond. Okay, or Dagashu will also be getting here. Okay, and then Tala, Kurichu, all you will get here. In what advantages it has in the dynamic measurement. So now here you can measure through a satellite, you can measure a power P1, V1, Q1, Q2, V1, V2 like. Similarly for all, and then additional advantage is it will also measure the del 1 and then del 2 if you go. Okay, all angular or phase angular differences you can measure as a del. Okay, this is using the satellite, and it will provide the timing pulses. Okay, this is how we measure. Okay, so locally measured phasor having a common reference time is transmitted to a load dispatch center. So whatever you are getting, you are transmitting to load dispatch center. But concept we are using is a new concept it is using is phasor measurement unit. Okay, PMU. So in next semester, final year, final semester, you will learn about what is meant by PMU. So for your information, in Bhutan, we have installed the PMU at the Tala, Chukha, Pasachu. Okay, I'm remembering only 3, but I will share. Okay, as soon as I get the more information with. But I remember around 7 PMU is installed in Bhutan. In generating station Tala, Chukha, and Basachu. Then Malbesi substation, then Nangkor substation, Tingtibi substation. So around 7 PMU has been installed, and they are collecting. Okay, BPSO is collecting all this data, and then they will estimate the power system state. And then based on their estimation, so they will recommend or they will advise the respective operator to perform different control strategies. Okay, so this is how we measure. And then just here I have given location 1 and 2. So in location 1, let's say Chukha, you can measure voltage, current, voltage, power, everything. And then in location 2 also we can measure this, okay, magnitude and Well, magnitude of these 2 waveform can be measured at 2 locations. Okay, so 2 location independently. The phase angular has to be obtained using a common clock in order to calculate the phase angle differences correctly. Okay, so easily you can measure magnitude, power, voltage, reactive power as well as real power. But if you do like this, then you will not be able to have an angular difference. But how you can measure angular differences? You should have a common clock in order to calculate the phase angular difference. So like this, you will have a one common clock. Okay, so which means you are starting from here, and you can measure this all phase angular difference. Okay, so phase angular difference between the two can be determined if a common timing pulse is transmitted to the location simultaneously. So which means, so in location 1, you see here, at this time it started, okay, transmitting, and then location 2 at the same time, okay, so it has been started like this. So then your waveform is, you can see here, then you can say that here it is a del 1 value, you can accelerate, let's say 90 degree, and then here it will be not be 90 degree, some other value it will be there, or okay, so then you can measure this, and then you can find that del 1 minus del 2, and then you can estimate the power system state estimation. Okay, so here all explanation about this I have given here. Okay, use of this phaser for line and equipment protection is perceivable, and then moreover this measurement may be used to detect or predict angular instability when the system is actually undergoing transient state. Okay, so in static state, if it is in transient state, we will not be able to measure this. Okay, but this using a satellite, so we can carry out this, and this can allow for quick control action to avoid complete failure of grid, means blackout. So it will prevent the blackout. And at present, that's why I said at present this system are not widely deployed, but in future they are likely to find greater use in real-time control and protection of power system. Okay, but they have said it is not widely used, but in Bhutan there are 7 PMU or phaser measurement unit installed. Okay, one is Chuka, Tala, Basachu, I feel. Then Nangkor substation, Malvesi substation, Ting TV, and then one. Okay, so I will share that slide with you all. Okay, so where it has been installed, but in final semester we will learn. But just now, what you have to know is you have to know how we will measure or how we will estimate the power system state by using a dynamic measurement. Okay, so that's all about today. So today we have learned about the power system state estimation definition, and then what are the methods or what are the different ways which we can estimate static and dynamic. So and then you know that how to carry out the power system state estimation in static state. Okay, so we can measure the P1 Q1, P2 Q2, V1 V2, and you try to calculate del 1 minus del 2, substituting in the basic formula. And then if you get the consistent del 1 minus del 2, then it means that we have estimated correctly. But if you get the inconsistent value, then we have to handle that error. Okay, so handling a error and bad data. So what you can do is you try to do an average, and another way you try to minimize that. But even doing this, what you have seen is if you are not able to record the data properly, or if there is a huge or major error exists in your data, then these two method will fail. So now if it fails, then what we have to do is we have to use this dynamic measurement using a satellites, and in this it says it will be provided accurately. And then that's why in Bhutan, that particularly BPSO has installed 7 PMU. Okay, so this one I will share with you that where it has been installed, PMU. And okay, so that's all for today. Okay, so if you have any query or doubt, so let me know.